You're muted, Professor.
Sorry, folks, that was my mistake. I was saying a lot of beautiful things that you couldn't hear. So I'm going to continue with talking about angular momentum. This is what we talked about on Friday, and that is the topic for today as well. So last Friday, we introduced the concept of electron spin, and electron spin is another source of angular momentum. It has the same kind of properties as orbital angular momentum. That is the picture you see here. You see an electron spinning around. It gives rise to orbital angular momentum. But the electron has another source of angular momentum, and that is spin angular momentum. And these two things are very much related because they are described by operators like L. L is the angular momentum orbital operator, orbital angular momentum operator. And there's also a spin angular momentum operator that's called S. And they have the same kind of structure, these operators. They have the same kind of eigenstates and eigenvalues, not the same states, but the same kind. They're similar in spirit. The same kind of rules that apply to spin angular momentum also apply to orbital angular momentum. So today we're going to use that fact and introduce a consequence of that, okay? Because if these two things are the same, if they have the same kind of origin or the same physics, then they may also influence one another. And that is exactly what is happening when the electron is part of an atom, because the electron will have orbital angular momentum and spin angular momentum. These two sources of angular momenta can actually reinforce one another, or they can also deplete one another. Okay, and that is an effect that is called spin-orbit coupling, and that spin-orbit coupling effect is influencing the energy that the electron can have. Okay, so there's an effect here called spin-orbit coupling that is having a consequence of on the energy that the electron can have in the hydrogen atom. Okay, so that's something we're going to look at right now. So here you see the picture again of the electron that is spinning around on a ring. It has a linear momentum p, distance r, and then that results in the angular momentum that is pointing upwards, as you can see in this picture. So this is, of course, the classical picture. This is not necessarily quantum mechanics. Okay, but there is a result that, or consequence of this spinning electron with this angular momentum. Maybe you know this from electromagnetism. If there is a charge that is going around in a circle, then that will induce a so-called magnetic moment. Okay, so there's a magnetic moment of a circularly moving charge. And so that magnetic moment has a certain magnitude, and we can specify that. So this is the magnetic moment, m, and it is a vector because it has a magnitude and it has a direction. And here is the relation between the magnetic moment and the orbital angular momentum L, which is this vector right here. So they are directly related, okay? The only difference between them is a prefactor, which is given here. It's E over 2me, where me, of course, is the mass of the electron, and there's a negative sign in front of it. That's because of the negative charge of the electron. This whole thing here, including the negative sign, is called gamma E. Okay, so gamma E times L, that is the direction and magnitude of the magnetic moment that the electron has as a consequence of spinning around. So if I now have an electron spinning around in an arbitrary direction, let's say it spins around on this particular circle, then the orbital angular momentum is directed in a slightly different way, in this way, okay? And that also means that the magnetic moment will be directed in that direction. Okay, so not necessarily aligned along the z-axis, because this one is not spinning in the xy plane, it's spinning in a different plane. But as we have seen with quantum mechanics, we can always make a projection onto our chosen axis, which is the z-axis, and then look at the projection, the projection of this vector onto the z-axis to determine the magnitude. Okay, so that is called mz. That is the projection of the magnetic moment now onto the z-axis. Okay, so mz is the magnitude of the projection of the magnetic moment on our chosen axis z. So in classical terms, again, this is a classical formula. The mz, the projection of the orbital or the angular momentum, sorry, I should say that differently. The projection of the magnetic moment onto the z-axis is proportional to the projection of the orbital angular momentum on the z-axis times the same gamma e. Okay, so this is the same prefactor that relates the magnitude and direction of the magnetic moment and orbital angular momentum, as well as their projections. In quantum mechanics, then, we have a certain magnitude for these projections. Classically, this Lz can be any value, okay, but quantum mechanically it cannot. Quantum mechanically, it can only have these values. Sorry. Okay, so these are the values that are allowed by quantum mechanics, and they are definitely quantized because ml is an integer. Classically, Lz can be any value, but quantum mechanically it cannot. It can only have integer values ml and then times h bar. All right, so and we can take these two quantities together, the gamma e and the h bar, and we call that minus mu b. Mu b is just a new constant that we defined that basically is proportional to gamma e times h bar, and that is defined as the Bohr magneton. So the Bohr magneton is basically telling us the relation between the projection of the orbital angular momentum on the z-axis and its magnetic moment on the same axis. Okay, so that relation is indicated by the Bohr magneton. Now, this is the magnetic moment due to the fact that the electron has a charge and that the electron is spinning around. What about the fact that the electron has a spin? Okay, so there's also a magnetic moment due to spin. Of course, this is analogous to what we just talked about. But instead of L, now we're talking about S. All right, so because it has S, because an electron has spin angular momentum, it also has a magnetic moment due to that spin. And the relation between the magnetic moment contribution from the spin is given right here. It's again gamma E times, of course, the spin, but then times another prefactor, which is called GE. Okay, and this factor has the magnitude of 2.002319. Okay, so it's almost 2, but not quite. Okay, so what do we have in the end? We have now, if we focus on the magnetic moment projected along our z-axis, mz. So think about this picture here. I'm just asking myself, there's a magnetic moment and it's directed along the z-axis. How big is that magnetic moment? Then it has two contributions. One, the orbital angular momentum will contribute, and that's given right here by this particular equation. And then also the spin angular momentum will contribute, and that's given by the equation right here. This is the same Bohr magneton, but now there's a prefactor in front of it, which is 2. For all intents and purposes, G equals 2. Okay, so how do we factor this in, and what are the consequences of these two sources of magnetic moments? So this is something that is, I already stated last Friday. We looked at the operators of angular momentum, okay? And we basically defined a general operator, J. J is an operator for angular momentum in general. So it doesn't matter if it's for L or for S. Any operator that has angular momentum character, I can summarize by this letter J. Okay, and we already concluded that there's eigenstates associated with this angular momentum operator. And I can call them J, which is related to the magnitude of angular momentum, and Mj, of course, are the quantized projections onto the z-axis. Right? So basically, the eigenstate is fully defined by these two integer values. Actually, the J doesn't have to be an integer value, but this can be a half integer as well, as we will see. The magnitude of angular momenta always follow this relation. no matter what the source of angular momentum is, spin or orbital angular momenta or any other source, this always holds. The angular momentum operator squared operating onto its eigenstates will generate eigenvalues that have always this quantity, right? That always have this value, j, and then between parentheses, j plus 1 times h bar squared. That is the magnitude square of the angular momentum. So basically, this is how big the angular momentum is. The projection operator onto the z-axis, we know, generates values, eigenvalues, when it's operating onto its eigenstates that have mj times h bar as their value. Right? So these are the projections onto the z-axis. The same thing as stated before. And then finally, there are relations between the different projection operators, namely the projection operators for angular momenta on the different axes do not commute, okay? In this case, you see the commutation relation between jx and jy, and it generates a value which is not 0. It's h bar times I times jz, which is a different operator, but this is a very odd result, okay? But it's definitely not 0. And that means that I cannot know something about jx and jy at the same time, right? But you can know something about the overall magnitude of the angular momentum and its projection, because those two operators commute. They have a commutation relation that produces 0. So I can know the projection and I can know the magnitude of the angular momentum. So this list here, these 5 statements, if you wish, are the definitions of what angular momentum is from a quantum mechanical point of view. If your operator fulfills these conditions, then your operator has the character of angular momentum. Both the operators for orbital angular momentum, L, and the operator for spin angular momentum, S, they both have these properties, right? They must, otherwise they are not operators for angular momentum. So, but what about a combination of 2 sources of angular momentum? Well, I can define a new operator that's called JC, where C stands for combined. Okay, and this combines two sources of angular momentum, namely J1 and J2. I don't know what they are, but they must both be operators that are angular momentum operators. For instance, L and S, as we just concluded. So let's say J1 is L and J2 is S. Orbital angular momentum and spin angular momentum. Now, if you make a combination of the two, then it turns out that this new operator behaves also like an operator that's an operator for angular momentum. That may sound trivial, but it's important to mention that, okay? The new operator, the combination of the two, is also an operator that fulfills all these rules, okay? Because it does, it means that the magnitude, not magnitude squared in this case, but just the magnitude, so the eigenvalues here, the square root of that is the magnitude of the combined angular momentum. And I can directly write down what that is. I don't have to compute anything. I don't have to think about the eigenstates or whatsoever. I know that the eigenvalues will have this value because it is a source of angular momentum. And that means it fulfills this condition right here. The projection is then, of course, always the MJC, which is now the quantum number for this new operator, times h bar. That is the projection onto the z-axis. So it works in exactly the same way as above. And there are 2 JC plus 1 values of this new value MJC. So it follows the same rules. The commutation relations are also the same. So for this new projection operator, for this new angular momentum operator, which is a sum of 2 sources, its projections, x and y, do not commute, as given by this relation here, which is the exact same relation as the one over here, right? There's no difference between the two. So in other words, this list of statements defines what orbital angular momentum is in terms of quantum mechanics, right? And if I make a combination of 2 sources of angular momentum in quantum mechanics. I can define a new operator, and this operator behaves exactly according to the same rules as above, right? So that's really good to know. We need to know this, otherwise we cannot move forward. Okay, so this is something general, but I want to make it more specific. I want to see what happens if I combine the effects of S and L, spin and orbit angular momentum. Okay, so we're going to combine these two things and see what happens. All right, so I'm going to now define a new operator. It's called J again. Very general way of writing, but that is fine. J is just the general way of writing angular momentum. And I say my new J is the combination of L and S. So spin and orbit effects are both included now to determine my total angular momentum. So my total angular momentum is the sum, or is related to the contributions from each origin of angular momentum, orbital and spin. So what I'm going to do now, I'm going to square this whole thing. You'll see in a moment why I do that. The result is below here. So the magnitude square, again, that is J to the power 2, is, of course, this one multiplied by itself, S multiplied by itself, and then the combination between the two, the cross term, okay? Twice S times L. That is the magnitude square of this new operator, the combination of the two. What I'm really interested in is this term here, okay? This term is the combination of S and L, and then multiplied here. This cross term is the so-called spin-orbit coupling term. Why is that so? Because this term here is simply the magnitude of the spin. This term here is simply L squared, which is the magnitude of the orbital angular momentum. So these two guys are just the sum of the previous origins, contributions of angular momenta. Okay, this term though is new. This term really relies on the coupling between the two sources. So there's an extra term here. It's not just the sum of the two. The magnitude is not just the sum of the two. There's also a cross term, and that cross term is the spin-orbit coupling term. An extra term that could, you know, make or break or move up or down the total energy of the electron due to the fact that spin and orbital angular momenta can couple. So what I'm going to do is I'm going to take this last term and isolate it. I'm going to take the same equation. I'm going to move everything else to the left. Okay, so J squared stays here. L squared, which is L squared. This is S squared. Okay, all of them I'm going to move. These two guys I'm going to move to this side of the equation and then divide the whole thing by half. Okay, and this is what I'm getting. So I get S times L equals half times J squared minus L squared minus S squared. All of these are operators, as you can see. Right? So this cross term here, the spin-orbit coupling term, is really what I'm interested in. What is the energy contribution of this term, this extra term that indicates how spin and orbital angular momenta couple, and thus change the overall energy of the electron in the hydrogen atom? So what I'm going to do now is see what happens when this thing, this cross term, operates onto one of the eigenstates of J. What are the eigenstates of J? Well, those are just simply J, Mj. Okay, these are the eigenstates of J. So when J operates on it, and so what I'm getting is the regular situation. Let's make this J squared because that's easier to write. J plus 1 h bar squared times J Mj. Okay, that's from the previous slide. It hasn't changed. So these are the eigenstates of this operator J squared. What happens if L squared is operating on J, Mj? Okay, or if S squared is operating on J, Mj. I can know this because J is a sum of L and S. So if J, Mj is an eigenstate of the square, That means that it must also be an eigenstate of the square of L and S, because L and S are components of J, right? So what happens is that I can write the following. I can write that this is L plus 1 H bar squared J mj. I can conclude that these eigenstates are also eigenstates of the magnitude for angular momentum for orbital and angular momentum for spin. Okay, J, mj. I'm going to use that fact in the next line of my derivation, comma, there. All right, so this is what I'm going to do. I'm going to operate on this eigenstate of J, and of course when it operates, and when J, the first part of this expression, which is J squared, operates on that state, which is the relation here, I'm generating J plus 1 H bar squared. That's this one. And then, oops, minus L plus 1 comes from L squared operating on the same eigenstate, generating L plus 1 H bar squared as the eigenvalues. That's the second term. And the third term, in exactly the same manner, is generated by the operator S squared, generating the eigenvalues S plus 1 H bar squared. Okay, so the important note here is that the eigenstates for J are also eigenstates for L squared and S squared. So I have here now a pretty nice result, okay, because all these numbers here, J, L, and S, are not operators, they are just values. They're just values. They're basically quantum numbers, okay, that are associated with the operators. So these are just numbers, and if I know these numbers, if I know the values of these quantum numbers, then I can just fill them out and calculate the magnitude of S times L. That means the magnitude of the spin-orbit coupling. What does that give me? It gives me the following. It gives me basically access to the spin-orbit coupling energy contribution to my problem. That's what I'm really interested in. Okay, so the spin-orbit coupling, SO stands for spin-orbit coupling. E, of course, is the energy. And you see this is exactly proportional to wherever is written above. This whole term here, okay, is the same as this term right here. Same thing. There's a new term in front of it. Okay, there's H times C. So this H bar is now actually H. C is, of course, the speed of light. And A with this little tilde on top is a constant that we will specify in the lecture on Wednesday. We'll write exactly what that is all about. But this A here is related to which atom you are talking about. So it's different for a hydrogen atom, it's different for helium, different for lithium, different for every single atom. Depends on a couple of ingredients, okay? But in any case, the magnitude of spin-orbit coupling energy is related to whatever these quantum numbers are. The J, the combination quantum number for angular momentum, L, the contribution from the orbital angular momentum, and S, the contribution from the spin. If you know all these things, you can compute the energy shift due to spin-orbit coupling. All right, so let's bring it into practice because it looks really, really abstract what I'm just talked about. So let's look at the hydrogen atom, and let's pretend, or let's consider that the electron in hydrogen sits in state 2p. Okay, so it sits in the p orbital, not in the s orbital, which is the ground state, but let's say the electron is excited to an excited state to the p orbital state. That's where the electron sits. This one simply means that that's the one electron in hydrogen. Okay. So I'm going to now consider if this electron sits in that state, what will be its exact energy? Okay. So let's consider then the magnitude of the spin-orbit coupling, right? Because the energy of the p orbital is, of course, the energy of the p orbital. But now I'm saying that on top of that, on top of the energy of the p orbital, there is an extra contribution, which is this spin-orbit coupling term, the term that we just derived on the last page. In order to calculate that spin-orbit coupling term, I need to know a couple of things. I need to know what these quantum numbers are, L, S, and J. So if I have one electron in the 2p level, That means that L of that electron equals 1. Why? Because that's the definition of a p orbital. Okay? If the electron sits in that orbital, it has a orbital angular momentum quantum number of 1. And of course, a single electron has always a spin quantum number of half. This is the spin quantum number. This is not its projection. Projection can be half or minus half, but the spin quantum number itself, S, is always 1/2. Okay, so these are L and S. So what are the number of states this electron can sit in? And this may be confusing to you, but let me bring this home. Let me first do it in a very abstract way and then tell you how you can think about this. The number of states in which this single electron can sit depends on the number of options it has in terms of L and the number of options it has in terms of S. In terms of L, as we know, there are 3 possibilities because it has ML states. How many ML states are there? 2L plus 1. And how many S states are there? 2S plus 1. Okay, so this is basically the number of states the electron can be in based on the fact that it has orbital angular momentum. And these are the number of states it can be in based on the fact that it has spin angular momentum. So 2L plus 1, 2 times 1 plus 1 equals 3. And this is 2 times half plus 1 is 2. So 3 times 2 equals 6. So there's 6 states in which this electron can sit. Now this, again, may look like a little abracadabra to you. Where is this coming from? It's not too hard, okay? Because if the electron sits in a p orbital, there are 3 p orbitals, right? 3. Because ML can be -1, 0, and 1. So there's 3 possibilities. This electron can be in a first, can be in a second, could be in a third. And that is the 3 here. That is the 2L plus 1. What is the 2 all about? Well, it can have spin up and spin down. Okay, so there's a total of 6 possibilities. There are 3 states, and I can put it either spin up or spin down. So there's 3 times 2, which is 6 possibilities for the electron to be arranged in the 2p state. Right? That's what the 6 is all about. But it's important to realize there's 6 possibilities of putting the electron in a certain way in a p orbital, right? Because 3 p orbitals, 2 spin states. Okay, so here's my situation, and this line here indicates just the state 2p. All right, it has L equals 1 and S half, and as we just concluded, there's 1, 2, 3, 4, 5, 6 states in which the electron can sit. I put these lines here, but these lines are basically overlap with this state because they all have the same energy, as far as I'm concerned. All right, so if we don't really consider spin-orbit coupling, all these 6 states will have the exact same energy, no difference between them. So there's degeneracy. This state has a 6-fold degeneracy. Okay, 3 because of 3 orbitals are available, and 2 because you can order the spin up or down. So 6 times degenerate. But this degeneracy can be lifted because of spin-orbit coupling. All right, so let's compute now what the spin-orbit coupling is. Spin-orbit coupling is of course related to the fact that L and S can combine, but they can combine in different ways. So let's see in how many ways the spin can actually be combined with the orbital angular momentum. The first way in which I can combine it is by simply adding them up. That means that the quantum number J, which is the quantum number associated with the total operator for angular momentum, J roof. This one does not have a roof. This is a value. This is an operator. This is the value, the quantum number associated with that operator. Its value depends on whatever L and S is. The sum of the two, of course, is 1 plus half. That is 3 halves. Okay, so I have one value for J that is 3 halves. Now, if this is 3 halves, I can actually do a couple of computations. The other combination is L minus S. And in general, as we will see next time, the way in which you can combine 2 sources of angular momentum is simply the sum, that's the highest possible value, their difference, which is the lowest possible value, and everything in between in integer steps. That's the so-called Clebsch-Jordan series, and we will actually consider that next time. But for now, we only have 1 particle, 2 sources, which means I can only add and subtract. Since S is half, the possible values are only 1 plus half, which is 3/2, and 1 minus half, which is half. There are no other options. There are no integer steps between 3/2 and half other than the one step itself, because they're separated by one integer value of 1. Okay, so the only way in which I can combine L and S, the quantum numbers L and S, is simply by their addition and their subtraction, producing two values for J. J can be 3/2 and J can be 1/2. J is the quantum number for the combined angular momentum. Why do I need to know this? Because if I do that, I realize that I have, instead of having 6 states that are degenerate, they could now be split into 2 new states. Okay, one that is indicated by 3/2 and one indicated by a combined angular momentum of 1/2. The magnitude of this state right here, okay, so this state right here, which is characterized by a combined angular momentum quantum number of 3/2, the magnitude of the total angular momentum in this state is 3/2 plus 1 times h bar, square root of this thing here, not of h bar, because it's already there. And that produces a total of 15/4 h bar. This is the magnitude, so 15/4 square root times h bar is the magnitude of angular momentum, the total angular momentum, when the electron sits in this state right here. Okay? Now, if you have a magnitude, you also have a projection, always. Always 2 things for angular momentum, a magnitude and a projection. What are the projections? Well, the projections run from 3/2 in integer steps down to minus 3/2. Okay, so here are the values: minus 3/2 h bar squared, minus half, plus half, and then 3/2. So there's 4 possibilities. Okay, I can only make 4 steps when I arrive to the plus value. From the negative value to the plus value, I can only make 4 steps, and those are the 4 possible projections of the total angular momentum when the electron sits in this state. So instead of having 1 state, in fact, there's 1, 2, 3, 4. There's 4 states here. So this state is 4-fold degenerate. Okay, so there's 4 little states here, 4 possibilities of putting the electron in a certain state. They all have the same energy, like they had over here, but here they were all degenerate. Now they're not. They're split into 2, where the upper one has a total number of projections, which is 4. That means there's 4 states that are degenerate when the electron sits in the state of combined angular momentum 3/2. But the other state here we haven't considered yet, so let's focus on that now. The magnitude I can compute: half times half plus 1, square root times h bar. That's going to give me an orbital angular momentum. Sorry, not orbital, a total angular momentum that has a magnitude of square root of 3/4 times h bar. You can see that if the electron sits in this lower state, that its total angular momentum is smaller than when it sits in the upper state. So there's a difference between the magnitude of the total angular momentum between the 2 states. What about the projections? Projections run from plus half to minus half in integer steps. That's only 1 step. So the projections have the value minus half times h bar, and then the other possibility is half times h bar. So only 2 possibilities here. So that means that the lower states right here have 2 little lines. There's 2 possibilities for the electron, as opposed to 4 up here. But lo and behold, the combination, of course, of the 2 states here and the 4 states on top is still 6. That's the same number as the degenerate states before I considered spin-orbit coupling. Okay, so what is the whole conclusion here? The conclusion is, previously, if I don't consider spin-orbit coupling, then if I put 1 electron into a p orbital, there's 6 ways of doing that, but all those 6 ways of doing it will give rise to the exact same energy of the electron. Right? So it's completely degenerate. Doesn't matter how you put the electron in a p orbital, it will always give you the same energy. If I include spin-orbit coupling, that is no longer the case, that all these states are going to be the same. I will find 4 states in which the electron combines favorably, if you wish, or unfavorably, depending on how you look at it, the orbital angular momentum that it has with its spin angular momentum. So there's 4 states now where the combined angular momentum is a little higher than the states below it, where the combined angular momenta of the spin and the orbital sources of the electron are now lower. Okay, and that leads to the fact that I have a 4-fold degenerate state here for this spin orbit coupled state, and a 2-fold degenerate state here for the lower spin orbit coupling state. So there's a splitting energy between these two, and I can compute that, and you can compute that from the formula on the previous slide. Okay, I just plug in the values for J. I know the values for L and S, so I have all the information to compute the energy of the 2 levels, subtract them from one another. We'll do that next time in more detail, but very briefly, that can give me the delta E, the difference between these 2 states in terms of the spin orbit coupling energy. And the value is 3/2 times H times C times this A tilde. Okay, again, this A tilde we will specify in the next lecture. Okay, so basically what we see is that indeed there's a splitting energy that is related, that is there because there is a spin orbit coupling energy. And I can compute exactly how big that is. All right, so we can determine how big the splitting is going to be because of the coupling of this spin of the electron with the orbital angular momentum that the electron has. Okay, so this is then what we get. We get a, let's say, electron that could be in the 1s state, or an electron that can be in a 2p state, but, and this is the new thing then, if it sits in a 2p state, it can actually be in 2 different states, all right? And you see these numbers, or kind of a symbol associated with each of these 2 states. These 2 states are the same states that we just determined on the previous slide. This number right here is the J number, the total angular momentum. You see the upper value has 3/2, the lower value has 1/2. But what does the P and the little 2 mean here in this kind of symbol? And that is basically what we call a term symbol. The term symbol has 3 ingredients. It has this kind of superscript, it has this capital letter, and then it has this J value here as a subscript. So how do we define that? It's defined as follows. This superscript is 2s plus 1. S is the total spin angular momentum. Okay. L is the total orbital angular momentum. And then J is the total angular momentum, the J we just computed. All right, so the total orbital angular momentum is called L. All right, that is the contribution, the total contribution that the orbital angular momentum brings to the picture. And they can have values. It could be 1, 2, 3, 4. All right, and we actually give those numbers names because, in analogy with the orbitals, which also have orbital angular momenta, all right, L equals 0 is called S, but not little s, it's called capital S now, because it basically relates to the total orbital momentum, not of a single electron, but can also relate to the orbital angular momentum of 2 or 3 or 4 electrons, as we will see next time. When total L, the big capital L equals 1, we get a capital P. When L equals 2, a capital D. And when L equals 3, capital F, and so forth. So this is in analogy with naming the orbitals. But these things don't mean the orbital. The orbital basically tells us what is the angular momentum, the orbital angular momentum of a single electron. This could pertain to multiple electrons as well. So it's a little different. The multiplicity is basically another word for 2s plus 1, where s is the total spin. Now, if I only have 1 electron, then that is simply 1/2. But if I have more than 1 electron, then this s value can have a different value, as we will see next time when we talk about helium, because helium has 2 electrons. The total angular momentum for 1 electron is the same as little j, and that was two possibilities that we saw. Oh man, what am I doing? 2 possibilities that we saw last time, and that is namely half and 3/2. Okay, so that's basically where these things come from, the term symbols. When the electron sits in this state, okay, when the electron is right here, then there's 2 spin orbit coupled states. This upper one is 4-fold degenerate. This lower one is 2-fold degenerate for a total of 6 states, as before. And the upper state is indicated by 2. Why 2? Because S equals half. 2S plus 1 means 2. Okay, so there's a 2 here. Capital P, the capital P relates to the fact that L equals 1. Because there's only one electron, little l equals 1. Little l is the same as capital L because there's only one electron, and that means it's a capital P. That's the same P as the p orbital here, of course. So this little p corresponds to the capital P here because there's only one electron. And then the J is the total angular momentum quantum number. There's 2 possibilities, 3/2 and then 1/2. So these are the 2 states that the electron can be in when it sits in the excited state of hydrogen. What about when it sits in the ground state? So let's say there's one electron that sits in the ground state. What is a term symbol? Well, it's already given over here. Can we understand that? Let's analyze this number here. It says the multiplicity is 2. Why is that? Well, because S, little s, is still 1/2. Little s is the same as capital S in the case of one electron. And that means that 2s plus 1 is 2. Okay, so this number here, this multiplicity number, tells us something about the spin states in which my system can sit. It can sit in 2 different states. What are the 2 states? Well, spin up and spin down. Okay, so the multiplicity tells me what is the number of spin states that my system can be in. 2. For one electron, you can only have spin up and spin down. That's what this 2 means. Okay, it's the same is true over here. The same 2 here means spin up and spin down when the electron sits in that state. The S here is the total orbital angular momentum. I have one electron. It has the quantum number L equals 1. That's the same as capital L in this case. And that means that this translates, sorry, it's 0 because it's in an S state. Okay, so that is a capital S. It sits in the S orbital. That means the orbital angular momentum quantum number equals 0, and that translates into an S. See? There you go. So that's the S, and then the J, which is going to be L plus S. Well, L equals 0, and S equals half, so that's going to be half, right? So that's the half right there. So this term symbol indicates the states the electron can be in when it sits in the 1s1 state, and these 2 term symbols indicate the states that the electron can be in when it's excited to the 2p1 state. The difference, of course, between the columns here on the left and these term symbols on the right is that the term symbols take into account the effect of spin-orbit coupling, and the notation here on the left does not. All right, so every time you see these term symbols, at least you know where they're coming from, and hopefully we will be able to work with them a little bit to understand if you have a transition from one state to the next, what is really going on with the electron? Where does the electron really go? Does it simply go from 1s to 2p, or is there more to the story? And of course, there's more to the story, as we will talk about next time. Okay, folks, that's all for now. This is already quite a bit, a lot of new notation once again, but keep your mind focused on the main principle, and that is that there are 2 sources of angular momenta, orbital and spin, and they can simply combine, they can help one another, they can also deplete one another, okay? And that is really what you see here as the result. In the upper one, angular momenta is reinforced, here it's depleted, okay? Here they help one another, here they don't help one another, and therefore you get 2 different possibilities of the total angular momenta that leads to an energy shift of the electron. You can imagine if you have higher total angular momenta that the energy will go up. If you have lower angular momenta, it will go down, and that is the origin of this effect. Spin-orbit coupling is a real thing. As you will see in hydrogen, the splitting energy is very tiny, so really it doesn't make a lot of difference in the end, but it makes a lot of difference for other atoms, such as lanthanides and transition metals, where these energies can be quite enormous and control the spectroscopy of these atoms. So that's why we have to talk about it. But that's for next time. All right, thank you, folks. I have no new information on what happened with the first midterm. We have to go through a lot of paperwork. We have to write letters. It has to be signed by the dean of the School of Physical Sciences, and it has to be submitted to check.com. They will consider it, and then they have to respond to our dean. It's a whole process. So this may take a little bit of time. So we don't know yet, but this process has been started. A lot of extra work again. We really don't want to do it, but we have to do it. So that's where we're at. If I know more, I will let you know. But for now, we don't know anything, so it may take a little bit of time. All right, folks, see you on Wednesday.